Okay, so in the rooted tree, given a binary tree, print the elements in a reverse level order. So what would that mean? So binary tree. Print reversed level order. So let's say there's not binary search tree, but binary tree. So I just take 4, 5, 6, 7, 8, 9. Suppose this is our binary tree. So by reverse level order, what we want to print is, I want to go, let's say 6, 7, 4, 5, 8, 9, 2, 3, and 1. So this is the output that I want. Okay, so how can I approach this? So I'm going essentially this way, and this way, and this way, and this way. So what do you see, like when you see that I'm going in this fashion? What kind of traversal this reminds you of?
Post-order traversal?
Post-order, you said?
Thing?
So post-order traversal is what? Post-order is left, right, and then root, right?
Yeah.
So then you would be going all the way. You would be doing 6, then 7. And then you're going where? You're going 5, right? Sorry, first is 4. The 4, and then 6, 7, 5. And then 2. And then you come on this side, and then you have 8, 9, 3, and 1. So it's not quite post order, as you can see, right? The main thing is that this whole jumping from here to here, right? 4, 5, and then 8, 9. This jumping is not not going to be possible, because the moment you do post order, it's a recursive traversal. So you're kind of forced to go down the subtree. So which particular traversal that allows you to go all the way and visit all these nodes at this level?
Breadth first.
Very good. Yeah, breadth first. But here we are saying it's a reversed order, right? So if the order had been not in this, the breadth first is going to be producing what? What would be the standard breadth first traversal will give you? So 1, and then, so what would be the BFS order give you on this? 1, and then
2, 3.
So 2, 3, 4, 5, 8, 9, 6, 7, correct? So one may think that I can just do breadth first and then store, and then I just print in the reverse order, right? Or maintain a stack, right? Also, and then I just pop the stack, and then that gives me the reversed order. That could be a potential thinking, but you can see that it's not exactly going to give you. So what's missing? So it's 1. What is the reversed order of this? 1, 3, 2, 9, 8, 5, 4, 7, 6. So this is just before reversal. So before reversal, this is what I want. So 1, 3, 2, 9, 8, 5, 4, 7, 6. What does this mean?
Go to the right first.
Exactly. So breadth first, traversal with right first. And then when you store, then when you reverse it, you'll get the intended output. Exactly. Clear? Okay. So find the nearest match of a given value in a binary search tree. This you have already done a lab on. Also, you have done your homework on. And in fact, that is what is the BFS supposed to help you with, the nearest match. Okay. Write a function to check whether two binary trees are structurally identical. How would you approach this problem? It's not that bad. So two binary trees are structurally identical. So first, what is it that you're supposed to? So this is our.
You just traverse two trees at the same time.
Yeah, you can say that. So what would be the common approach that can help us here? So checking whether two BSTs are structurally identical. So you have one binary tree, you have another binary tree. You have root 1, root 2, two roots. So your starting point is clearly, so you can see that you can pretty much smell recursion here, right? The base case being if the R1 is equal to null pointer and R2 null pointer, right? Then it is returning true. The question is, what is the inductive step? So of course, this has to match, right? R1 has to match R2. But what is it that we are matching? You're not matching R1 pointers, right? So we are matching the key, right? And
Wait, but I thought we don't really care about the values. We only care about like the structure, right?
okay, so fair point. I mean, structurally identical typically can also, yeah, you're right. It's a question like whether we want to also match the key or not, but you're right. Like probably we don't need to match the key. Okay, that's a fair point. So what should we be matching then? So we should be calling. So suppose this is called same, right? So suppose this is our R1 and R2. So this is our recursive function. So we can call same on what? The left subtree has to match and the right subtree has to match, right? So we can say R1 left, right? And R2 left. And similarly, the R1 right and R2 right. Correct? Then that should kind of recursively take care of it. That makes sense?
Yeah, it's pretty brilliant.
And then we are done. Okay, so I think can handle these questions also similarly, because it's just summing elements, finding the size. Let's do some complexity analysis problem. So you know lower bound, upper bound, and order functions. So big O notation is signifying the upper bound, lower bound is omega, and I had mispronounced it as sigma in some lecture before, but it's omega. Lower bound and upper bound is big O, and the order notation is the big theta. And I mean, these kind of questions are pretty simple. You just look for what is the dominating term. So clearly the dominating term is n cubed, right? So if you want to find a tight upper bound, then it will land up in order of n cubed, and lower bound will land up in log n, and big theta will end up also in n cubed. Okay, let's solve some recurrence equation just for practice. So for sorting algorithm below, so this I just wrote down a very straightforward partition based algorithm, right? So here you want to sort L and returning L dash. So if n is equal to 1, actually this should be n L comma n, so that we know the n. So if the length is 1, then it's the same. Otherwise you would like to split into two non-empty sets, L1 and L2. And then you sort the individuals, and then you merge, right? So the question here is that what if I had partition in the beginning versus in the middle? So what does that mean? So let's say, so essentially this is my list, right? So if I partition in the beginning, that's what it would mean. It has the first term and it has the rest, right? So it is 1 and n minus 1. Okay, so if suppose I'm splitting in this way, how does the complexity looks like? So T of 1 is going to be clearly 1, right? Now you can say big theta of 1. Now when there is T of n or n greater than 1, then what happens? So we do sorting of L1. So this is T of 1, right? Because we have partition in this way. This is partitioning with kind of partition in the beginning, and we are trying to see the effect of that. So for this one, it's going to be T of n, T of 1, and for this one, it's going to be T of n minus 1 plus the merge operation, and we know that merge operation is order of n. So then what would be the complexity looking like? So T of n minus 1, because this is order of 1, plus order of n. So how do we solve this? So we can, at every step, we can start now going down the path. So n minus 2. So we are substituting n with n minus 1. So order of n minus 1 plus order of n. Okay. If you go one step further, then it's going to be 1 n minus 2 plus n minus 1. I'm just dropping the order notation here, so you can see where it is going. So where should I land up in? I somehow need to bring it down to this as 1, right? I mean, if I have to generalize it, I would write down as.
No, I'd like some.
Okay, I think there is a, what is muted. Okay. Okay, so I want to land up in n minus k, right? And then this is going to be n minus k, then plus 1, plus dot 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 up to n. I somehow want to make this as 1 because I know what is the value here. So n minus k is going to be equal to 1 when n is equal to k plus 1, right? So we can write t of 1, and we can see this is going to be k plus 1. Okay, so it's going to be k plus 1 minus k plus 1. So effectively, this is going to be 1 plus 2 plus 3 plus dot 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 plus n. And this we know, n into n plus 1 divided by 2. So this is basically order of n square. So in other words, if we take the algorithm and we split in this non-uniform way, that 1 and then n minus 2 terms here, then it will result in n square complexity algorithm. But what if I partition in the middle? Then what do I get as the equation? So then I would get t of n is equal to t of n by 2, right? Because I'm partitioning in the middle. So this one, so this is the beginning part, and if it is in the middle, the split will be looking like this. So here n by 2, and here we have n by 2. So t of n by 2 plus t of n by 2, which is 2 times t of n by 2, plus order of n for merging. And we also have t of 1 is equal to 1, or big theta of 1. So what do we do here? We do 2 times, we expand again. So how do we expand? We substitute n with n by 2. So we can say 2 times t n by 2 square, right? Because I substituted n with n by 2 plus order of n by 2. Okay, plus order of n. Okay, let's see where it goes. So this is going to be equal to 2 square times t n by 2 square plus 2 times n by 2, that will be order of n plus order of n. Okay. So this means what? So now, if I write one more term, it would be t n to the power 3. We can see that, plus order of n plus order of n plus order of n, right? So this is going 3 times, which is the same as the power. So if I have to generalize it, I can write 2 to the power k t n by 2 to the power k plus order of n plus order of n plus dot 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 plus order of n, right? This is repeated k times, right? But I want to bring this down to the level where I understand what is the value, right? So I know that t of 1 is order of 1. So when will this term be t of 1? When n by 2 to the power k is equal to 1, which means n is equal to 2 to the power k. Okay, so I can substitute here wherever I see 2 to the power k as n. Now this terms becomes t of 1, after I substitute n equal to the power k, and this becomes essentially k times n. But what is k here? K is equal to log base 2 of n, right? So therefore, this becomes n times 1, which is n, plus k is log base 2 of n. So this is n log n, right? Now this is the dominating term clearly. So therefore, this is order of n log n. Okay, so this essentially we saw that depending on how you are partitioning, the same sorting algorithm can lead to either order of n square complexity or n log n complexity. In fact, this is what is the complexity for merge sort. And that's the algorithm that was describing here. Okay, so in terms of the sorting, we have.
Wait, in the first,
Go ahead.
sorry, in the first call, you plugged in 1/2, right?
Say that again.
In the first iteration, you plugged in to n 1/2 to get the, yeah, that line.
Yeah, here we are saying that if you are partitioning in the beginning, right?
Mhm.
You're just leaving one and then rest like that. If you're
Oh, sorry,
partitioning,
the middle partition.
yeah, this is the middle.
So like, if you can scroll down below a bit.
Yeah.
Um,
Did I write down middle here? Yeah, I wrote down middle here. Yeah, this is where it starts.
yes, so you right there, you plug in for n 1/2, I believe, or n over 2, you said?
Yeah, this is essentially T of n by 2 for
Mhm.
sorting this half. T of n by 2 is for sorting the other half. Right? First half, second half, plus
Mhm.
merging. This is merge. First half, second half, and merge. That's what this is.
Oh. Okay, that makes sense.
All right. So let's see what else can we do here. So sorting algorithms, you can definitely go through all the sorting algorithms that are discussed in the class. You should definitely look into the time complexity analysis for each of those algorithms. And so given an array of n elements, design an algorithm for checking whether there are repeated elements. This is an interesting question. How would you, now this is, you're already getting a hint because I put it in the sorting section. So if you have an array of n numbers and you want to check whether there are repeated elements, what would be your approach? I mean, if you try to do it in a brute force manner, it will result in n square complexity.
Would you do it for a quick sort and then see if adjacent
Yeah,
elements are the same?
Exactly. So that would be one way of approaching it, which is better than brute force, you know, definitely better than brute force. Now, of course, one can apply hashing here a little bit to even reduce the complexity further down. Okay. Given an array consisting of only zeros, ones, and twos, design an algorithm to efficiently sort the array. This you should be able to immediately say what it is, because you have done a lab assignment with that kind of. So 0, 1, and 2, which means that, yeah, counting sort, exactly. Okay, so let's see heaps. What are the minimum and maximum number of elements in a heap of height h? This is problem number 4. So heaps, when is it minimum? So heap, let's say heap. of height h. So minimum number of elements. When is it going to have minimum number of elements? How would the structure look like? So heap generally has a complete binary tree, right? It's typically this kind of structure, right? When is it going to have a minimum number of elements? So this is our height h. So this is actually showing the maximum possible number, right? So max is when it's filling up the whole height, right? With all the nodes. So it's a complete binary tree, right? There's a complete binary tree. So we know if its height is h, the total number of nodes for a complete binary tree, we have done that analysis. It's h plus 1 minus 1, right? But that's the maximum. That's easy. What would be the case when it is minimum? How would it look like? So let's say this is the h. It will have 1, just 1, right? That would be the minimum number that you need. So what would be the number of elements here? So this is h minus 1, right? So we take 2 to the power h minus 1 plus 1, that is 2 to the power h minus 1. That is the total number of nodes in this, plus 1, right? Plus this 1. So that is equal to 2 to the power h. So there will be 2 to the power h will be the minimum number of elements. Question number 5, let's see which one. Given a min heap, how would you find the max elements? Find the max element, not sorry, elements. What would be the max element given a min heap? So we know that in a min heap, the max element is residing where? So we know that this is minimum in a min heap, right? Max is here. Is it? Max should
Yeah,
be
the
here.
bottom right.
Exactly. But the point is that it can be, the tree can look like something like this. So it can be here,
All right.
right? So how do we get to that layer? So if this is the total number of count is count, right? So we know that count by 2 is immediately going to give us, count by 2 is going to give us where? Like if this is the count by 2 is going to lead us to this guy, right? So we start from count by 2 plus 1, which is going to be this one, to count. That would be the range in which you're going to look for max value. So this is the index range for looking for max. So max search. All right. This is an interesting question. Given a big file containing billions of numbers, design an algorithm to find max 10 numbers. I mean, I can give you some time to think. So the moment you see any question which is asking you to give the max 10 numbers, what you should be thinking along the line of priority queues, which means you should be thinking about heaps. So now here, because there are billions of numbers, you want to now adjust the complexity a little bit in trying to think how to approach this. So you can actually here, you can partition it into, let's say, groups of 1000. Okay. So you take the first group of 1000, you create the heap out of it, right? because the moment you create a max heap out of it, fetching the max element is straight away going to max 10 elements out of that. You can fetch it and it's going to be log of n, right? So you keep doing extract max operation 10 times on the set of 1000. So you got the max 10 numbers, but that's only out of that set of 1000, right? So what can you do with that? So now you choose 990 out of the rest and you add these 10 numbers to it and do the same thing again. And in this way, you can actually arrive at a solution very efficiently and very smartly. All right. It was just a trick question. Okay. So we have gone through graphs, many different problems. Write an algorithm for checking whether a given graph has a simple path from a given source node to a given destination node. So you can do a depth first walk to see if you're able to reach the destination node. It's going to be straightforward. And likewise, counting the simple paths from a source to a destination. These are all different varieties of ways you can walk the graph. Okay, we talked about the cycle detection, both for directed graph and undirected graph. We talked about the single source shortest path problems. Okay. Next, so these hashing questions are a little, you can say, interview style questions. If you like, we can quickly go through it. So design an efficient algorithm to find the first non-repeated character in a string. So let's say, let's do a couple of problems here. So first, what does it say? First non-repeated character. In a string. So typically the character set happens to be total 256, right? And that's what we want to take advantage of here. Which is a very simple application of hashing, very similar to the counting sort. So if you have to find the first non-repeated character out of a string, some string. So you can maintain essentially a count of 256, right? Where you can pretty much index because of the ASCII character set. So you just run for I equal to 0, I less than str length plus I, and you initialize count to 0. Sorry, count of I to 0. And then again, run the for loop, the same span, and you increment the count. So how do you increment? Because everything is indexed. So you do ASTR of I. So every character is occupying the index. So it's very similar to the counting sort. So once you have done that, then the rest of the checking is just running another for loop where you just check if count corresponding to the A str of I is essentially equal to 1, which means that there will be only one instance of that character. Then you return str. Otherwise, you return maybe -1. The next question is very similar. It's about first repeated character. So you have to find the first repeated character. You can make the check here. First repeated character. Okay, so next question is also very similar to the question of the previous one, in the sense that it's also similar to the hashing. So given an array of n numbers, present an algorithm which displays all pairs whose sum is s. Now, anything that you do with brute force, it will lead to sort of n square complexity if you don't use hashing. So how would you approach this? So just let's do this one last, and then we. So the question here is that given an array of n numbers, display all pairs whose sum is s, right? So you can scan all the inputs and create a hash table, right? And then you scan again and check whether the sum minus your corresponding I exists in the table, right? Because that element plus AI will be equal to S. So with just order of n complexity, you're done. And the next question you can now figure out, it's exactly the same kind of pattern. So here I just listed some interesting question that that you will see a direct practical application of these topics that we have covered. Okay,